here I wrote down for you in this shorthand notation our normalized solutions. So here are the normalization constant. 1, 2, 3 stands for first, second, and third solution. And so here again, we have this exponential prefactor. And let's now compute the asymptotic of this solution at z tending to plus infinity. For simplicity, we'll consider z a real parameter, and we'll study asymptotic just at plus and minus infinities. Right. So first thing we notice is, of course, the non-trivial exponential function, namely the exponent, which is by now quite familiar to you. It's a typical Airy-type expression. So we already know how this saddle structure looks like. So there are two saddles at points plus and minus square root of z. And the only difference from the Airy function case is that there is a branch cut here, which slightly complicates things. So let's see how the whole thing comes about. So we define the steepest descent directions, which are given by the second derivative. So for t equals to square root of z, the argument of the second derivative is pi, and the steepest descent direction equation is as follows. So that's a horizontal line. And for t equals negative square root of z, their argument of the second derivative is 0, and the steepest descent direction is a vertical line. So here they are, two saddles. And the first saddle is right inside the branch cut, and the steepest descent direction is as follows. But now, from the very structure of the saddles, of course, it's obvious how we should modify and deform the contours to get the asymptotics. The third contour should be placed in such a way that it passes through the saddle in the steepest descent direction, which is quite easy to achieve, just like that. So that's the correct deformation of the third contour. And the first and second contours can be simply deformed in the combination of two straight segments, right? Like we did for the computation of the normalization constant, because here precisely the straight line from 0 to plus infinity passes through the saddle in the steepest descent direction. And now I'll just give you their leading exponential expression, and you can figure out all the details, the other details by yourself, and write down the final answer. So the value of the exponent at point t equals square root of z is simply 2/3 of z to 3/2. At this point, and at the other point, minus square root of z, it's simply minus 2/3 of zeta to 3/2. And now we have the leading behavior of all our solutions. So u1 and u2 will obviously be proportional to e to 2/3 of z to 3/2. And the third solution will be given by our minus square root of z saddle and will be exponentially suppressed at large values of z. And with your permission, I'll just present you with the final answers for the asymptotics at large and positive values of z. Here they are. Так, пардон, это я последнее предложение, мне надо переговорить, я их даже не написал. Это будет их домашнее упражнение. Поэтому with your permission будет по-другому сформулировано предложение. And with your permission, I'll leave you all the details of the computation as your homework exercise, and I'll give you just the answers and their, in the supplementary materials to this lecture. Right, so now let's study a slightly more interesting case where z tends to minus infinity. And to this end, we need to slightly redraw the picture of all our saddles, because the saddle will be positioned, the saddle will change their position. And now the equation for the saddle stays unchanged, but the position of the saddle is changed due to the change of sign in z. So now t equals to square root of z, or rather I square root of the modulus z. So now these are our new positions of the saddles. Let's figure out the steepest descent directions. They're slightly modified. So the argument of their second derivative at point at the upper point is minus pi by 2. So the steepest descent direction equation is as follows. And here we have 3/4 of pi. So that's the steepest descent direction for the upper point. And for the lower point, it's symmetric. The second derivative is has an argument which is simply pi by 2. And the steepest direction is pi by 4. Okay. So here is our pi by 4 direction. And now the legitimate question is, how do we define the asymptotics in this case? Well, again, the deformation of their upper and lower contour is almost obvious, because the upper contour can be deformed into the combination again of two straight lines. One of them passes through the saddle in the steepest descent direction from in the up-down way. The same thing is true for the lower solution, because again it passes through the saddle in this steepest descent direction. So gamma 1 and gamma 2 behavior is mostly obvious. And again, the leading exponential factors will be easily computed, and it's your homework exercise. However, the non-trivial thing is just what is going to happen with gamma 3 solution, with the third solution, because we can deform the contour, the third contour, so it passes through their lower saddle and the upper saddle. But here we have a branch cut, and the question is, what's going to happen now? Well, obviously, in the vicinity of the branch cut or the branch point, the behavior of our exponent function is simply zt. And since z is negative, the steepest descent direction in the vicinity of the branch point is positive 1, this one. And now, obviously, you feel how the whole thing is coming about. So you deform the third contour, so it passes through the lowest saddle in the steepest descent direction. Then you have to circumvent the branch point. So you approach it along the steepest ascent direction and leave it in the steepest descent direction, which is positive direction in this case, and continue with the contour which it passes through their upper saddle. So that's quite unusual deformation, probably the only non-trivial thing in this exercise. And now we could compute both contributions from the saddles and from the branch point. Well, first, probably the easiest way is to compute the contribution from the branch point. In the vicinity of the branch point, our exponent function is simply zt. And our solution, this contribution, is split into their combination of two contributions from the lower bank of the contour and from the upper bank of the contour. So this contribution comes from the lower bank. And from the upper bank, we have identical contribution, but with different value of their this t function, t2 beta function. And of course, we have this here a multivalued function, and we defined its regular branch in a natural way. So we considered that the g of t function, which is 1 over t to beta plus 1, is positive when t belongs to the upper bank of the branch cut. So you have to take into account the additional phase of this g of t function as you go along the lower bank of our branch of this branch cut, and it will give you just some 2 pi I factor multiplied by beta. But these are, of course, nothing but their gamma function type expressions, and the answers is, of course, 1 over modulus z times minus beta times some prefactor, which you are supposed to compute at home. So the contribution from the branch point is just the power law behavior. Now let us compute the contribution from the saddles. So that's a branch point. The saddles are here and here, and first we compute the value of our exponential function at points plus minus I square root of modulus z. And we just plug it in here and get their standard behavior. For plus sign, we get 4/3 I modulus of z to 3/2. And that's for plus sign, and for minus sign we get the same thing with minus sign. So each saddle gives their complex conjugate expression, and the final answer will be proportional to the contribution of the both of them. And the value of g of t function at the saddle will be simply 1 over square root of beta, the square root of z times beta plus 1. So it's from their upper saddle and identical contribution from their lower saddle. There will be, of course, additional pre-exponential factor, which is the square root of 2 pi divided by our large parameter. But in this case, well, there will be actually none. So the whole contribution is proportional to the cosine of 4/3 of z times 3/2 plus some phase, which is defined by our steep descent expression, and the whole thing has the prefactor of modulus z to beta plus 1/2 in the denominator. So depending on the value of beta, we have different asymptotic behavior of our third solution. For example, if beta is positive, then their leading solution will be, so the leading behavior will be defined by the branch point, and it's going to be just a power law behavior. But if b is negative, then the principal contribution will be the oscillating cosine type contribution, which stems from the contribution of the saddles. So that's kind of non-trivial. So obviously, the whole analytical structure of our differential equation changes when b changes from positive to negative values. And it will be your home exercise to figure out exact phases and all the prefactors in all these asymptotics. That's it.